From this video onward, we are going to discuss about the problem of finding shortest path between two vertices in a graph. Now let's first look at a real-world example which will emphasize the need for such an algorithm. Now this slide shows you the road network map of the city of London. And our task is to find a shortest path from one location to other. Let's say from Paddington Station to Heathrow Airport. Now solving this problem in real-world application, like in the Google Map, involve many complexities like dynamic weight change for edges depending on the traffic and the traffic predictions, and path analysis depend on vehicle types, and lots of other optimizations. But if we keep aside these complexities, we are left with a graph which has locations and junctions as vertices and road as edges as shown in this graph. Therefore, we can use shortest path algorithm we are going to learn in this section to solve this particular problem. There are many variations of shortest path problem. Our main problem is single source shortest path problem. Here, given a source vertex, we are going to find shortest path to each of the vertices in the graph from source vertex. In single destination shortest path problem, we are focused to find shortest path to a given destination vertex from each other vertex in the graph. Now, by reversing the direction of each edge in the graph, we can reduce this problem into single source shortest path problem. In single pair shortest path problem, we are finding shortest path between given two vertices. Now, this problem is a sub-problem of single source shortest path problem. Therefore, it has same worst case running time as single source shortest path problem. In all-to-all shortest path problem, we are going to find shortest path between each pair of vertices in a graph. Okay, let's define our shortest path problem now. Shortest path between vertex u and v, or delta uv, is the minimum weighted path between vertex u and vertex v. To find shortest path problem, we first have to focus on some key point in our graph. Let's see what are those now. Our graph may include negative weight edges. And that's fine, and there are ways to find shortest path in a graph which has negative weight edges. But if a graph has negative weight cycle like this one, then we will not able to find shortest path for that particular graph. In this graph, between vertex E and F, there's a negative weight cycle. Now if you travel through cycle between E and F, we can see that the summation of all weights are -1. In fact, in this case, it is -3. Therefore, in each iteration through this cycle will result in decrement of distance for each of these E and F vertices. Therefore, we will not able to find minimum path because the distances are always decreasing. So, if our graph has negative weight cycle, then we say that the shortest path is not defined for that particular graph. Okay, now let me present you two important steps which we are going to follow in each of the algorithm for finding shortest path. The first step called initialization. In this step, we will set source vertex distance to 0 and all other vertices distance to integer type max or infinity, and predecessor variable for all the vertices will be set to null. The second step is called relaxation of an edge. For that, we pass start vertex of the edge which we call u, and end vertex of edge which is called v, and weight of that particular edge to function called relax. Now here, if the end vertex distance is greater than the start vertex distance plus weight, then we are going to modify the end vertex distance to start vertex distance plus weight, and we are going to set end vertex predecessor to start vertex. For example, for the edge in the left side, we have end vertex distance as 9, which is greater than the start vertex distance plus weight, which is 7. Therefore, we are going to update the end vertex distance to 7 and predecessor to u. But however, for the example in right side, our condition will fail, therefore no updation will happen. Okay, these are the basics we need to know in order to solve the shortest path problem. In the next video, we are going to discuss about solving the single source shortest path problem. Thank you.